So who thinks they got a beat on it? Anybody? No, it's too bad. This is going to be the kind of stuff you have to do. You can't hold your hand on everything. You know I can still surprise you with all the practice you guys have had. You got to kind of start looking at what's being asked of you. Let's just consider from here to here, right? Just that one. Did you do conservation of momentum? So you know what this velocity's got to be, right? Okay. So you have an expression for that now. About a quarter of V naught. All right, so let's start with that. Now, there's anybody who needs me to do that part of it? Okay. Carlos, what has momentum before the collision? And what would its momentum be? That's how do you calculate momentum? All right. That's going to be hard then. Do you have it in your notes somewhere, anywhere? The whole point of the unit? That's how you calculate momentum. I'm going to need you to bring something to the table, okay? Anything. So, you want to tell me now what the momentum of the block is? Carlos will never ask a question in class again, shall I? All right, I will tell you everything, but I have fear for you on Tuesday. That's it. That's the momentum of the block. All right. That has to equal the momentum of the block and wedge. Now, block and wedge are moving with the same speed. So the momentum of the block and wedge will be the mass of the block and wedge together. So I'm thinking m for the block, 3m for the wedge, and they have a combined velocity v. So v equals 1/4 v naught. Now we know how fast both of these things are moving at this particular instant. It's not going to be moving like this for very long. It's going to be like this for just an instant as the block makes it up to the top of the wedge and then starts coming back down. But both of them are moving at this moment, and they're both moving to the right. Energy is conserved here because there's nothing to take energy out of the system. It's not a collision where I made noise, so I just slid right up the top of the ramp. So if it's just conservative forces acting on the system, and gravity is a conservative force, this conserved energy. So what kind of energy did we have in the system here? Kinetic. And that's just the kinetic energy of the block. So that'd be 1/2 m v naught squared. What kind of energy do we have in the system here? We have gravitational potential. That's just the block. Only the block is higher than it was before, correct? And it's some height above where it started. I'm going to label that h. That's what we're looking for, the height of the block. So that'll be mgh. But that's not the only kind of energy in the system now, is it? What other energy does the system have? That's kinetic, because both blocks are moving. So I'm going to add to that 1/2 m, and this is going to be both m's here. So 4m times their velocity squared, but their velocity is 1/4 v naught squared. This isn't that hard, is it? It's just knowing what you need to do, because we've never seen a problem like this before. Now, can you work this out for h? I will point out all the m's cancel out. That's just a convenience factor because I chose to make the thing a multiple of m, but I'm hoping so. We're just trying to collect our terms here. So a few things. I would probably cancel all the m's out first. Just get rid of them, get them out of the way. I've got 1/4 squared, but then I multiply by 4, so that's just 1/4, right? I'm talking about right here and here. So that's still going to be just 1/4. But then I multiply by a half, so it's 1/8. So that's that term. And I have still GH. And then 1/2 V0 squared. Just doing algebra now. This isn't very exciting. I'm going to subtract 1/8 from 1/2. I think I'm going to get 3/8. Again, I'm not particularly scared of fractions. And that's it. This is the answer. So I'll divide by G. And we'll get 3 V0 squared divided by G. I'm sorry, 8G. There. Yeah, I think this is a perfectly acceptable question. There's more to it, though, isn't there? We have to figure out V1 and V2. Now there's no easy way to talk about this. V1 and V2 are independent velocities, but momentum and energy are both conserved here. This is an elastic collision. So you have to solve for V1 and V2 using the fact that both momentum and energy are conserved. So that one might be a little more straightforward since we talked about elastic collisions, but we didn't work that out. So I'm not going to work the whole thing out because I think there's other examples we need to see today. But I think we could set that one up and then you guys could work it out at your leisure because it's just algebra once it's set up. So let's set up that question, okay? I don't need anything that's here for this next portion, so I'm going to kind of remove the stuff that's in the way. So if you start writing stuff down, tell me and I'll slow down. But I'm trying to go pretty slow as it is. No? All right. Now all we need to talk about is this part. So we're going from here to here. This is a conservation of momentum and a conservation of kinetic energy question. So the momentum part, we don't have a whole lot to go on, but we have a little bit. I don't necessarily know that this block is going to the left. I'm not going to assume, so I'm going to make all the velocities positive over here and just put m v2 plus 3m v1. If I work it out and it comes out to be negative, then I'll know, but I would just put all the velocities as being positive. Again, we have to solve for v1 and v2, and we can't do that here because we have two unknowns. So let's go ahead and go to the next relationship. That's going to be the kinetic energy of the system has to be conserved. So 1/2 m v naught squared has to be equal to, both of these objects have kinetic energy, so 1/2 m v2 squared plus 1/2, don't make this mistake, it's 3m v1 squared. And there it is, you got two equations and two unknowns. We can get rid of all those m's. That'd probably be a nice start, wouldn't it? And I'd also get rid of all the 1/2s, right? You can see that you can do that too. So that will simplify this to be, and by simplify, I use that word very broadly. It's not particularly simple. But V naught equals V2 plus 3V1. And then V naught squared equals V2 squared plus 3V1 squared. There, that's the heavy lifting. Now you just got some algebra. You want to eliminate one or the other. I would probably, if it were me, and if you wanted a suggestion, I would eliminate V2 between these two. And here's why. And only some of you are going to understand this, so I'm speaking only to a small group. But you notice that the bottom equation is a quadratic, which suggests that there'll be two possible answers for V1 and V2. You have one answer for V1 and V2. The initial conditions are one of the sets of answers. And the initial conditions are that the original velocity of the block was V naught, and the original velocity of the wedge is 0. So although there are two answers for V1 and there's two answers for V2, one of the answers for V2 is V0, and one of the answers for V1 is 0. Knowing that going in means if you eliminate V2, one of your roots is going to be 0, and it'll be easier to solve. So I would eliminate V2. You'll find it to be easier. But this is just algebra, so I don't find that particularly interesting. So if you do great, have fun. Do you see how this is just a modified version of the same question? If it's a friction-free surface, I could ask what is the maximum compression of the spring? It's the same as finding the height. The same kind of problem. The maximum compression of the spring will occur when both the M box and the 3M box have the same speed. So there'll be an intermediate condition where this block will have slid over to here, compressed the spring, but now both of these blocks are moving to the right at some combined velocity. The energy is stored in the spring, and then the spring releases, and both blocks have their own independent velocity. Does that make sense? Now there's a future version of this where the block sticks to the spring, and then the blocks oscillate as they move, and you have to figure out what the oscillation period is. But that's a second semester topic, so we'll wait for that one. But for this one, this problem is done the exact same way of the problem we just did. In fact, almost, because I gave it all the same numbers, the only difference will be you'll have 1/2 m v0 squared equals 1/2 k x max squared plus 1/2 4m 1/4 v0 squared. That's going to be the only difference because everything else is the same. So it's an interesting question. These questions pop up from time to time. The trick is knowing that the maximum height attained and the maximum compression of the spring occur when the system has the velocity of the center of mass. That's what it amounts to. So, all right. There are more questions to ask like that, and you know, there's a variety of things that could be. It could be the force from the spring on the box, the force from the wedge on the box. All of that stuff are possibilities and things that they might do. So when you look at these problems, there's a range. All right. It says this is a released old exam question. Several of these are. So this was asked on the AP exam. This one's actually pretty old. This one I think dips into the 80s, so it's a pretty old test question. But this is fair game kind of stuff. It says a bullet of mass m and velocity v0 is fired toward a block of thickness L and mass m. The block is initially at rest on a frictionless surface. The bullet emerges from the block with a velocity of 1/3 its original velocity. Determine the final speed of block m. I don't think that one's particularly hard, but yeah, that's a conservation of momentum question. So I think since it's a conservation of momentum question, what I'll do here is we'll just make it take up a little less space. I like to kind of talk about what this looks like. So we're going to have the bullet emerging from the brick, but now it's got v0/3, and the brick is probably moving too. So we just don't know what that velocity is, but that's what they want us to figure out. This is a pretty clear conservation of momentum question, because it's a clear collision. One object contacted another object. So I'm going to go with the momentum of the system beforehand, mv0, has to equal the momentum of the system afterwards. The bullet still has momentum, and the momentum of the bullet is m times v0/3. But now the brick has its own momentum, which is mv, and we are solving for this velocity here. So I will subtract the bullet's momentum from both sides and get, let's see, that'd be 2 mv0/3, right? 2/3. Is that good? And that equals mv. So I'm going to solve that for v and get 2 mv/big M. There. What negative?
Like when you subtract the m v0/3.
I used the negative. I subtracted 1/3 from 1. Yeah? Oh, sorry. Sorry. right? I did okay? All right. Except for missing the 3 there at the end. All right. If instead the block is held fixed and not allowed to slide, the bullet emerges from the block with a speed of v naught over 2. Determine the loss of kinetic energy of the bullet. Okay. So the block is held fixed, and it's not moving after the bullet emerges, but the bullet emerges at a speed of v naught over 2. And we want to find the loss of kinetic energy. All right. So the original kinetic energy, right? So kinetic energy before minus the kinetic energy after would be the loss of kinetic energy. So I mean, I'm not reading anything more into that. This question actually can be asked about 3 different ways. This is just a straight up subtract. But there's also stuff like finding the percentage of energy lost or the percentage of energy that remains, stuff like that. So if you want, we could talk about all 3 of those possible ways of being asked. So if we just do the loss of energy, this is going to be 1/2 m v naught squared minus 1/2 m 1/2 v naught squared. So right, we're just straight up looking at how much energy is lost. So half squared is a quarter. 1/2 times a quarter is an eighth. So 1/2 minus an eighth is 3/8, right? We just did that. So this will be 3/8 m v naught squared. So this is how much energy is lost. Now, a common way of asking this question is to ask what is the percentage of energy lost. And that would be finding the difference in energy but dividing by the original amount of energy. This would be a percentage. So if we did that here, we'd get 3/8 m v naught squared divided by the original, which is 1/2 m v naught squared. Again, this would be the percent lost. And that's actually asked way more common than just how much energy is lost. So the mv naughts in this cancel out. And it looks like we're going to get 6/8 or 3/4 or 75% lost. But like I said, that's a way more common question, is to calculate percent lost. All right, question C. Assume that the retarding force of the block material exerts on the bullet is constant. In terms of L naught, what minimum thickness, L, should a fixed block of similar material have in order to stop the bullet? Okay. Do I need any of the stuff that's here for you guys, or are we good? Can I get rid of it? So I just want to get rid of this stuff. All right, so now we're asking a different question. It's saying to us that the material that the block is made out of applies a retarding force the same way no matter how wide the block is. We want to know how wide does the block have to be to fully stop the bullet. They're saying the block is going to be fixed. So I think we can all probably agree that the block is going to have to be wider than it was before, right? Because it wasn't wide enough to stop it before. I think what we're looking at here is a work energy question. Because in the last one, the work equaled the change in kinetic energy, correct? Now, we don't know what that force is, but we know that force is going to stay the same. And in the last one, the force times L, L naught, that's how large the block was. Right? This is how much work had to be done because the force on the bullet occurred while it was passing through the block. This work is also negative because the force on the bullet is this direction while the bullet is traveling to the right through the block. Right? So it's F dot L dot cosine of 180. Does that all make sense? And that equaled negative 3/8 m v naught squared. Is this the amount of kinetic energy we lost? Now, the reason I'm doing this is this can give me an expression for what the force must be. So if I solve this for F, I can find the force from the material. 3 mv naught squared over 8 L naught. That is the force from the brick on the bullet. Is that all good for you guys? Because we want to find out how wide does the bullet have to be, how wide does the block have to be to stop the bullet? So now that I know what the force on the bullet is, I can say, all right, bring me a brick that is L wide to stop the bullet, which means I needed to have a change in kinetic energy of negative 1/2 mv naught squared. I want to fully stop the bullet. And this has to equal F dot L, right? The work on the bullet. And I want to find this new L. Does this make sense to you guys? All right. Well, I know what the force is. I know it's still cosine of 180, so I'll have 3 mv naught squared over 8 L naught times L times cosine of 180 equals negative 1/2 mv naught squared. Yahoo! Cosine 180 and the negative sign go away. The mv naught squared and the mv naught squared go away. And it looks like I will have L equals 4/3 L naught. If my arithmetic is correct, I think that's it. I'm pretty happy with the fact that it is a bigger brick. So that's good. I'd be a little bit frustrated if it was 2/3. Then that wouldn't make any sense. But yeah, I think that's it. Wow, this is a good one. I like this question. This is a good one. When the block is held fixed, the bullet emerges from the block with a greater speed than when the block is free to move. Explain. Can you guys explain it? I think I can explain it. What do you got, Thomas? What's your explanation? If you did the problem, you already had to do that part when the stopper was in place. And none of that portion of the problem is any different now that the stopper is removed. So you had all of this before. Like that. And this is 200 newtons per meter. This is 8 kilograms. This is 2 kilograms. And then we have our lump of clay, which is 0.1 kilograms. And do they tell us how fast it's launched? Or do you have to find out how fast it was launched? You had to find it. Did you guys find it out already? That way I don't have to do that work, or do I have to do that work too? Or do you not have any confidence in your answer? So let's backpedal a little bit. The stopper's in place. The clay hits the 2 kilogram block. The 2 kilogram block and clay compress the spring 0.4 meters. Is that what I'm reading? All right. So there's two parts to this problem. So let's work the problem. I don't want to redraw this a billion times. So let's just say that we have this part where the block and clay have compressed the spring 0.4 meters. So at this moment, there was elastic potential energy in the spring, and it's the only thing that has energy. So that's going to be 1/2 K delta X squared. And that has to equal the kinetic energy of the block and clay just before they start to compress the spring, which had to be 1/2 times 2.1 times V final. So this is after the collision. All right, so this is how we figure out how fast the block and clay was traveling after the collision. So 1/2 of 2.1 is going to be 1.05 V final squared. Actually, why even do that? How about just cancel out the 1/2s? So 2.1 VF squared equals K is 200 times 0.4 squared. Is that good? Okay. 0.4 squared is 0.16 times 200. I don't know. You is it 32? What's that? It is 32? Excellent. The old man can still add. That's good to know. 32 divided by 2.1, so somewhere just a little bit less than 16. And then take the square root, so somewhere around 4. Somebody want to give me something better than that, or I'll just go with 4. Okay. All right, so this is how fast the block and clay are moving directly after the clay strikes the block. So let's tuck that over here for a minute. And I don't need any of this work anymore. So, but for those of you still writing it down, I'll put it over there in the corner. So momentum was conserved when the clay struck the block. And it's only conserved the instant before the clay strikes the block and the instant after the clay strikes the block, because once the block starts to moving, momentum is no longer conserved because an external force acts on the clay and the block. That's the spring. Does that make sense? So we only have this instantaneous moment, but the clay, 0.1, and its velocity, v, plus the block, which is 0 momentum, had to equal 2.1 times 4, which is actually like, what, 3.9, or whatever that was. So here we go. 2.1 times 4 is 8.2. And this is 0.1 v, so v equals 82. We have a winner. Good job. Sorry.
Okay, I just forgot to multiply it by the mass.
Gotcha. All right, so now we can do the problem that you actually asked about. Take the stopper away. Whee! All right, so we really didn't have to figure out the speed of the clay, I guess. We just needed this velocity here. But let's go ahead and go with that because we've got it. So this is how fast the clay and block are moving directly after the collision. So state the principles that can be used to calculate the velocity of the 8-kilometer block. Well, here's the thing. When the spring regains its original length, that is an elastic collision. So we're going to have the momentum of the system before, which is going to be 2.1 times 4 equals the momentum of the system after the collision, which both the block, the little block and the big block are going to have independent velocities at this moment. And it's when the spring regains its original length, so the spring is no longer applying a force to either block because the spring is neither compressed nor stretched. You guys follow that okay? All right, so that'll be 2.1 v1 plus 8 v2. That's the momentum part of the problem. But energy is conserved in this case because any of the energy that would have been lost was actually in the spring. So when the spring regains its original length, it gives that energy back to both the blocks. So we'll have 1/2 times 2.1 times 4 squared, the original energy in the system. This, you could have also used the 1/2 kx squared for the energy that was in the spring, but the x here is different, so this is the best one to use. This has to equal 1/2 times 2.1 v1 squared plus 1/2 times 8 v2 squared. I set up, but did not solve, a set of equations that could be used to figure out the velocity of the block after the collision. And just like before, I would eliminate v1 because v2's original velocity was 0. So one of your roots will be 0.